Hello folks, welcome to MTenjung. Here in this video, we come up with an interesting mechatronics project that is a tooling planar robotic arm. So to do this, first we will model it using SolidWorks. We will export the model into MATLAB using Simscape multibody link so that we can build a control algorithm and simulate the real behavior of the robot both graphically and using MATLAB Explorer. So in this video, we will help you understand the modeling and simulation of robots using SolidWorks, MATLAB and Simulink, and it doesn't need in-depth knowledge of MATLAB to understand what we are going to do. If you are new to MATLAB, it is a perfect opportunity for you. And by the way, don't forget to subscribe, like and share this video so you will get notified every time we release amazing video like this one. So without further ado, let's get started.
This is the robot that we are going to do on this video, and we will start using sketch command. We will start on the first part on the base, and we open new parts, and on the top plane sketch a circle and make the dimension 150 millimeter and add a feature, extrude both base and extrude it 20 millimeter. Click on the edge and choose fillet and set it 5 millimeter, and you can have any type of colors, and choose front plane and sketch, choose line and draw a center line. To do that, right click and construction geometry, and again type S and draw a circle at the top and draw an arc for the body of the first part. And make sure these two arcs, the circle and the arc, are tangent to get a better surface finish at the end, and give it a dimension. And define the height of the first revolve joint to 100 millimeter and this circle to 30 millimeter. And it is not still fully defined, so define the arc, the first arc radius and the second one. Then using powertrain command, we can remove unwanted lines and close this sketch, then extrude it on mid plane, and for better surface finish and strength, we can add a chamfer on the edge. You can also use fillets. Select this face and sketch. We can draw a circle. Set the diameter of this circle as this circle to 20 millimeter and extrude it around 5 millimeter. This is the hole that will be inserted from the next link pin. And save this part and make sure there is no gap between the words. And the first part is finished, and let's move to the next. Open new part, and we will make the second part. To start, open new part, and choose front plane and sketch. Choose a midpoint line, and if you select this midpoint, you will drag it on the both sides, and you can escape this and define the length of this line. And draw the circles. Define the diameter of these circles. And to connect this, choose 3-point arc and select those two lines and one on the empty space, and you can have this beautiful arc. And make sure this arc is connected tangentially with the circle. And define the arc radiuses. And you can extrude it. Select every boundaries and make sure you open mid plane and set the extrusion 15 millimeter. And select this face, and you can have a chamfer on both sides and click OK. and we can also add some feature for better look on the face, on this face, so that you can sketch on it. Then extrude this 5mm, and by removing some components from this, we can have a better look of the arm. Okay, make it the center line as a construction line, and drag this line and connect it, and make it symmetric. And the angle between these two lines are 30 degrees. And this distance is 20. And reduce this fillet and select this edge, and exit the fillet command. Reduce a little bit. Okay, undo this. And choose circular pattern, and the axis of the pattern is on the center, and entities to pattern is this sketch. Choose this point, and choose the number of instances, how much we need this shape. I think it's low, it looks good, and extrude this. Since it is a vertex at the end, it will give us an error. So let's draw a circle with the diameter 4, and we can proceed. Choose extrude both base and select this face, okay. Choose this face and make fillets. Still the fillet is large, so reduce the number. This cutout is used for connection of the pin from the next joint. And at the back face, we draw a circle set the diameter to 10 and extrude post base. Then we make this pin to connect from the previous hole. Then save this next part. Again, make sure there is no space other than underscore. And for the next part, let's save as this part for S. Rename it as the third part 3 arm 2. It looks similar, a little bit different. Apply some appearance. Then we can edit on this graphics area. Double click on it and type 50mm. And as you see from the design tree, we can delete some components like cut, extrude feature, and also this sketch. And this looks like it. Now we will draw a gripper like structure just to mimic the gripper. It is not a real one. If you want to make a real gripper, I have made a video. You can also find the link in the description. And make it tangent. Then we have to select and mirror on the opposite sides. Okay, first we will define every undefined lines. Now the sketch is fully defined. Next one, we will select all this sketch and choose mirror entities and mirror about this line. And as you see, the shaded area shows that the sketch is closed, so with that we can extrude it and choose mid plane and make sure it is merge result is checked, and you can click OK. Now this is the last part that we need for the assembly of the robot. Okay. And the robot's assembly is here. First open the assembly and make sure it's plain white, and insert this components and choose the first one, the link 0, and place it around here, and similarly insert some components, the arm 1 and arm 2, place it anywhere, okay. The next one is we have to assemble this. Now the parts are imported. Make sure this first link is float to better move for proper visualization. And I think it is good position, and let's mate this top plane to the top plane, and we can fix it now. As you see, the coincidence is grayed down so that we can delete it, and choose those faces and make it coincidence. Choose this circle, and in the inside circle make it concentric mates. Then this will act like this. It will be coincidence with that. And similarly drag this and select this circle, and this one make coincidence mate. So these mates will work, these coincidence mates will work on the MATLAB as a revolving joint. For other projects, make sure you select the appropriate mates for export, since every type of mates are not supported in Simulink. And save these robots as this name. Okay, the robot mechanical model is now finished. The assembly is finished, so that we can proceed the MATLAB. Run the MATLAB as an administrator. To call when we export the SolidWorks model into MATLAB, we can call the MATLAB. Before I start an in-depth explanation and modeling of the control algorithm, let me give you a brief overview of the projects that we are going to do up next. As you can see from the control diagram, there is a clock signal that helps us give a time variable to determine the desired trajectory of our robot in time. The desired trajectory is in a plane, since it is a planar robot, so it gives us two variables as an output, xd and yd. As you can see from the code, both variables have the same input u, which is the clock time that we have seen. And the next one is the inverse kinematics block that takes the desired robot trajectory xd and yd and gives us an angular position of the robot to follow its trajectory with respective time. The angular positions are θ1 and θ2, and these two angular positions are actuated by a motor, either by a stepper motor or a servo, that needs to be controlled using a controller. In this case, we will use a PID controller, and that will take the error signal and tries to eliminate it to get the desired trajectory the same as an actual trajectory. The error signal is created by subtracting the desired angular position of the robot θ1, which is the output of the actual motor from the robot mechanical model, and the desired angular positions that come from the inverse kinematics block. And the final block diagram is the forward kinematics block, which uses just for visualization purpose. It takes the angular position of the robot and it gives us the position of the end effector of the robotic arm with the respective of time. You may have been confused about how can I get the formulas that guide the robot, like inverse and forward kinematics. And I will give you an in-depth mathematical analysis to find its forward and inverse kinematics of this robot in a separate video. The link is in the description below.
First, let's go to add-in and activate the Simscape multibody link. And after that, we will go to we will check out our parts. The mates are only these four mates that guide the robots, and after we check this, okay, the MATLAB is opened now, and we go to tools, and under tools Simscape multibody, and export it as Simscape multibody. Then you can find your directory to save the XML file, and this XML file will help this robot, will hold this robot's properties. Make sure there is no space between the letters. Okay, this is our directory. Let's copy it and paste on the MATLAB command window. Under this bar, we will paste the directory of our project. As you see, it is blank now, since we doesn't export the model still now. It is blank. Okay, the process is now activated, and after some time we finish the exports. Then these are the step files that holds the robot, and the XML file is that integrate those step files into some components, and we can import these step files into MATLAB Simulink using SimImport command. Then you can copy and paste the name of your project, then enter. And after some time, it will load the robot model, and it generates a Simscape multibody link or Simscape multibodies. As you can see, this is a Simscape model of or Simulink model of our robots that we have did using SolidWorks. Then make sure you save this file again. It will save as a Simulink. Okay, we can proceed. First, let's run the model if it works or not. As you see, it is compiling now. It shows us good results. Here is our model in Sim Explorer, in Mechanics Explorer. Still, it is not loaded. As you see now, the robot is going like crazy. So we have to control this using a PID or another mechanism. Okay, to do that, go to library, Simulink library, and user defined function, and let's add the functions. Add two block parameters, and the other one that we need is a clock. And right click and add to model, and the other one is the XY graph. Similarly, right click and add to the model, and the next one is a PID controller. Just type PID and enter. Then the PID controller is here, then it added to the block. Then the sum to subtract the error. Okay, I'll position those far away from the model to better visualize it. Okay, these Rivoli joints are the robot joints that is to be provided by inputs. The actuation and the torque is automatically computed, and we have to sense the position of the robots. So the position on the sensing block, the position is made as an output. And similarly for the second joint, double click on it, and on the actuation, the torque will be automatically computed and the motion will be provided by input, and the sensing, we only sense the position of the end effector. Okay, double click on the empty space and type Simskip to Simulink to physical converter and physical to Simulink converter. Then connect this output to this and connect this. Similarly, copy those two files, and let me rename the joint, the first joint 1 and joint 2. Copy these two and connect them.
and on the empty space type in. This will be as an input and output. Connect it the outputs, copy and paste, connect these two, make sure the position is only, the sensing is the position only, and rename this as theta 1, and for the second input is theta 2. And the outputs, rename the first output as theta desired 1, and this is the desired 2. And select all these and make it create a subsystem. Then rearrange this. We don't need those, so we delete these outputs and inputs. Then we need only this subsystem that holds the robot mechanical model. Okay, then we will go to the others. First save the file, bring the function block and copy and paste it 3 times, then connect the clock, arrange the same PID to better location for connecting the lines. We need one for theta 1 and theta 2. Then we need 2 PID controller. Arrange it properly. Then double click on the function. Double click on the function and write this code. As you see, this is the desired trajectory, and with the input U. After we save it, the block will be changed into 2 outputs with 1 input. The 2 outputs are XD and YD, and also rename it as a desired trajectory. As you see, these 2 outputs are connected with the same block. Then double click on the function tool and rename this function name. First, the outputs are theta1 and theta2 with the name of the function is inverse kinematics with an input xd and yd. Then define the length, the angle, then save this code. Then go to Simulink and arrange this. Then rename this as inverse kinematics. The function one. The inputs are actual XA and YA. The name of the function is forward kinematics with an input theta1 and theta1A and theta2A. Then give the length and write the formula for the forward kinematics. Then go to the Simulink model and rename it as forward kinematics. Expand the block, and now we are going to connect every element. Then XA connected with XY graph. Then this theta desired is connected to the forward kinematics block. Then the PID controllers will be connected. First connect the XD and YD. Resize it. Connect these two. Then connect this sum block to the second PID, the PID to this mechanical block, Then drag this, right click and drag this and connect to the same block. And connect this XY graph. The XD and YD are the desired trajectory. Then from the desired trajectory, using XY plot, we can see how the robot will go. And make sure on the mechanical model, connect at the input terminal the PS converter. Make sure the second order filtering is on, unless otherwise it doesn't work. Since we use ODE 45, make sure the filter type as second order filtering and click OK. As you see, we have to rename this as minus, since we need the error. Then save it. Make sure our code is right and we didn't make any mistake. Run it. It's now compiling. Okay, there is an error, as you see. There is an error on the code, the undefined L1. So we go to the inverse kinematics. Then the inverse kinematics. Under the inverse kinematics, there is some error. Let's see the error. Okay. Then on the inverse kinematics, there is undefined function variable L1 on the line 5 and column 45. Okay, so it guides us to this position on line 5 and column 45 is around here. As you see, when we select it, other L1 is not highlighted. When you select this, they all are highlighted but not this one. So make sure we name it. Then save it. Now to check it, click on the L1 and still doesn't show that on the line 5 L1 is not highlighted. So copy it and paste. One and L are nearly similar, that's why I'm confused here. And let's run the model. Still there is another error. Okay, on the forward kinematics block theta 1 a, the variable theta 1 a is not defined. On the forward kinematics, the fourth line theta 1 a. As you see, there is an error here. Then delete this h. Now it seems good. Here there is another mistake. Now it's better. Okay, save it and go to this and run. As you see, the model is working properly. The time is now running, the model is running, but it is so slow. And as you see, the input, the desired input on the XY graph is shown, the output is also shown, but it is cropped. So we have to resize the XY plot, since the XY plot is only showing us from +1 to -1 on the both x and y axis. So we resize it as by first double click on the block, and the minimum will be 0 and set the maximum to 3. And again for the negative side, set it to 0 and 1. And for the output similarly, as from this diagram you see sample time as -1, that will be inherit the previous sample time from the model, not the actual -1 sample time. As you see, the output is nearly tracing the input trajectory, but clearly there is an error. So we have to tune this PID controller to better mimic the desired trajectory. Okay, to tune this PID, double click on the first PID block. As you see, from this Mechanics Explorer, there is a smooth animation, but this simulation is not correct. So with this PID controller block parameters, we have to change some components or some parameters to better see the outputs. So that makes the proportional as 10, the proportional gain as 10, and let's see how the proportional gain will change the response of the system. As you see from the plots, here are the two plots. If you compare it, now we get a better value from the previous one. The proportional gain will reduce the steady state error. If you compare it with the previous outputs, the steady state error is very large. By just tuning the PID block parameters on the PID block parameters, the P only, we can get better. So again, by changing another parameters like the integral parameter to 20,
we can get a different result. Okay, let's run it and see how it will work. As you see from the input output plot, this simulation takes a little bit time. Now the result is better from the previous one. The error is now eliminated. There is no overlap between the lines. Okay, there is still an initial jerk, and also there is another tuning mechanism, that is automated tuning. Just press the tune button and we can have a desired control over the robots. Okay, when we press the tune button, the robot mechanical model is non-linear model. So PID is linear model. So we have to change this non-linear model into linear. So the PID block by itself will linearize the model and approximate it to a linear one. Okay, it takes some time. Okay, now the tuner app is opened, the PID tuner app. As you see, the previous block response and the tuned response, we can change the response time faster or slow, and we can also play on the behavior of the transient response by just sliding the sliders at the top, and you can see the overshoot settling and rise time on the show parameters. Then if you get a better control or a better results, you can update the block just by pressing the update block button and close this window. Then as you see, the PID parameters are updated. And for the second controller, we will do similar procedures. Just press tune button and the plant will be linearized, and after linearizing it will pop up the tuner app, and by sliding the sliders we can get a desired reference. As you see, I make it faster and robust, but it is not an optimal one. There is 4.13 overshoot, that is very little. I make it just for better simulation, not the real one. Then save it and run the model. As you see, now the time my computer is stuck because of the D controller. The D parameter in the PID block takes much computationally intensive, and we have to make it to 0 since it is very computational intensive. Even if it is very small number, it takes much core of our PC, so make it 0. Or you can use a PI controller. Now save it and run the model. Now if you see, the model is running faster than the previous one since we make 0 on the D parameter of the PID controller. There is a large jerk, but the reference is better. The reference tracking is better from the previous one. This jerk could happen because of we make 0 of the PID, the D parameter. Then close this, and we can see the mechanism, how it works on the Mechanics Explorer. As you see from the graph, there is a jerk. That jerk is also displayed here. If you watch it closely, there is a rapid movement. Okay, thank you very much. As you see from the model, there is a giant jerk that disturbs the robot's trajectory. So, if you know the correct answer how to remove this jerk, write the answer on the description below. Thank you very much.